Hello everyone, my name is Sham Padik. I am a student of BSc Chemistry Honours first year. Today I will be reading chapter number 2, Periodic Properties, from the book Modern Approach to Inorganic Chemistry, written by Dr. S.P. Johar. So the chapter begins. The concept of periodicity has acquired the key position in the study of inorganic chemistry. No other generalization competes the periodic table of the elements in its ability to simply systemize and rationalize known chemical facts. At present, about 112 elements are known which have numerous properties and form millions of compounds. The periodic classification of elements has extremely simplified their study. Many different forms of the periodic table have been proposed depending upon the purpose for which the table is used. However, the most commonly used form is known as long form of periodic table. Let us briefly recapitulate the development of periodic table, its salient features as already studied in earlier classes, and important periodic properties and their applications. Point number 1, development of the periodic table. Since the beginning of the 19th century, scientists have been trying to find a basis of grouping elements having similar properties. Though several scientists, namely Lavoisier, Dobrenier, Newlands, Mayer, and Mendeleev, attempted to find certain regularities among elements, the first important attempt to divide the elements on the basis of their physical and chemical properties was made by a German chemist Lothar Mayer and a Russian chemist Matthias Mendeleev. They observed that when the elements are arranged in the order of increasing atomic weights, the elements with similar properties recur at regular intervals. Mendeleev gave a law named as the periodic law. The law states that the physical and chemical properties of elements are periodic functions of their atomic weights. The Mendeleev's classification gave him so much confidence that he boldly left certain spaces or gaps for undiscovered elements. By considering the properties of the adjacent elements in his table, he predicted the properties of these undiscovered elements later on which these elements were discovered. Their properties were found to be exactly similar to those predicted by Mendeleev. For example, gallium and germanium were not discovered at the time. When Mendeleev formulated his periodic table, he not only predicted the existence of these elements, but he also estimated their properties. He named these elements as Eka aluminium and Eka silicon because he believed that this would be similar to aluminium and silicon respectively. When chemists discovered these elements, Mendeleev's prediction of their properties proved to be remarkably correct. Modern periodic law. In 1912, Moseley showed that the physical and chemical properties of the atoms or of the elements are determined by their atomic numbers and not by their atomic weights. This acceptance of atomic number as the important characteristics of an atom led to the modern periodic law, which may be stated as the physical and chemical properties of the elements are periodic functions of their atomic numbers. Consequently, when the elements are arranged in the order of their increasing atomic number, it is observed that the elements of similar properties recur at regular intervals or periodically. As a result of this, the elements fall in certain groups and led to an arrangement called the periodic table. With the modern periodic law as the guiding principle, many new forms of the periodic table have been proposed. However, the general plan of the table has remained the same as proposed by Mendeleev. Of this, the most commonly used form is known as long form of the periodic table. The long form of the periodic table, position of elements in the periodic table. The most widely used periodic table these days is the long form of the periodic table. This is constructed on the basis of repeating electronic configuration of the atoms when they are arranged in the order of increasing atomic numbers. Long form of the periodic table is given on next page. Structural features of the long form of the periodic table. The long form of the periodic table consists of horizontal rows called periods and vertical columns called groups. These are discussed below. Periods. A horizontal row in the periodic table is called period. In terms of electronic structure of the atom, a period constitutes a series of elements whose atoms have the same number of electron shell, that is principal quantum number, and there are 7 periods and each period starts with a different principal quantum number. Elements of first period. The first period corresponding to n equals to 1 is unique because it contains only 2 elements. This is not surprising because first energy shell has only one orbital, that is 1s, which can accommodate only 2 electrons. This means that there can only be 2 electrons in which 1 and 2 electrons are present in first energy level. The period contains hydrogen 1s1 and helium 1s2. Elements of second period. The second period contains 8 elements because for n equals to 2 there are 4 orbitals, 1 2s and 3 2p. In all, these 4 orbitals have a capacity of 8 electrons and therefore second period has 8 elements in it. It starts with lithium Z equals to 3 in which 1 electron enters the 2s orbital. The period ends with neon Z equals to 10 in which the second shell is complete 2s2 2p6. Elements of the third period. In third period corresponding to n equals to 3, there are 9 orbitals 1 3s, 3p and 5 3d. However, we know from energy level diagram for multi-electron atoms chapter 1 that 3d orbitals are higher in energy than 4s orbitals. Consequently, 3d orbitals are filled after filling 4s orbitals. Hence, this period involves the filling of only 4 orbitals, 3s and 3p, and contains 8 elements from sodium Z equals to 11 to argon Z equals to 18. Elements of fourth period. The fourth period corresponding to n equals to 4 involves the filling of 1 4s and 3 4p orbitals. 4d and 4f orbitals are higher in energy than 5s orbitals and are filled later. In between 4s and 4p orbitals, 5 3d orbitals are filled which have energies in between these orbitals. Thus, in all 9 orbitals are to be filled and therefore there are 18 elements in fourth period from potassium Z equals to 19 to krypton Z equals to 36. Elements of fifth period. The fifth period, like the fourth period, also consists of 18 elements. It begins with rubidium Z equals to 37 with filling of 5s orbitals and ends at xenon Z equals to 54 with the filling up of the 5p orbitals. Element of sixth period. The sixth period contains 32 elements Z equal to 55 to 86 and successive electrons enter into 6s, 4f, 5d and 6p orbitals. In that order, it starts with cesium Z equals to 55 and ends at radon Z equal to 86. This is the long form of the periodic table in which we can see the groups and the periods. Now we'll discuss about elements of seventh period. The seventh period, though expected to have 32 elements, is incomplete and contains only 23 elements at present. This also provides a theoretical justification for periodicity occurring at regular intervals of 2, 8, 8, 18, 18 and 32. These numbers, that is 2, 8, 18 and 32, are also called magic numbers. The first 3 periods containing 2, 8 and 8 elements respectively are called short periods. The next 3 periods containing 18, 18 and 32 elements are called long periods. The number of elements and the corresponding orbitals being filled are given in table 1. Period first, orbital below, period n, orbitals being filled up, number of electrons or elements in the period. Period first, n1, orbitals being filled up 1s, number of electrons 2 and or elements in the period 2. Second, 2, 2s, 2p, 2 plus 6 which gives us 8. Third, 3, 3s, 3p, 2 plus 6 which gives us 8. Fourth, period fourth, 4s, 3d, 4p, 2 plus 10 plus 6, 18. Period fifth, 5s, 4d, 5p, 2 plus 10 plus 6 which gives us 18. Period sixth, 6s, 4f, 5d, 6p, 2 plus 4 plus 10 plus 6 which gives us 32. Period 7th, 7s, 5f, 6d, 7p, 2 plus 14 plus 10 plus 6 which gives us 32 groups. A vertical column in the periodic table is known as group. In terms of electronic structure of the atom, a group constitutes a series of elements whose atoms have the same outermost electronic configuration but they have different number of total electrons. There are 18 groups in the long form of the periodic table according to the new recommendations of International Union of Pure and Applied Chemistry IUPAC. The groups are numbered from 1 to 18. Previously, these were numbered only from 1 to 8 in Roman numbers as A and B groups. Both the systems of numbering the groups are given in the periodic table. However, the old convention is still used in many books. The first 2 groups on the extreme left and last 6 groups on the extreme right involve the filling of s and p orbitals respectively. These groups represent the main groups on the periodic table and are numbered as 1, 2, 13, 14, 15, 17 and 18 corresponding to general configuration of ns1, ns2, ns2, np1, ns2, np2, ns2, np3, ns2, np4, ns2, np5, ns2, np6 respectively. The elements present in these groups are known as normal or representative elements. The first three periods containing 2, 8 and 18 electrons involve the filling of only s and p orbitals, but the fourth period involves the filling of 3d orbital also. This results into 10 more groups. These 10 groups lie in between first 2 and last 6 groups. See periodic table between groups 2 and group 13, because 3d orbital are filled after 4s but before 4p orbitals. The elements present in these groups are called transition elements. The name is derived from the fact that they represent transition change in character from reactive metals, elements of group 1 and 2, on one side to the non-metals, elements of group 13 to 18 on the other side. The designation of group as A or B is purely arbitrary. The assignment of all the transition elements metals to B groups has an internal consistency as well as historic precedent. However, IUPAC has recommended that the groups be numbered 1 to 18 left to right, from the alkali metals group 1 to the noble gases 18. There are two more rows at the bottom of the periodic table. This row consists of 14 elements after lanthanum, Z equals to 57, and 14 elements which follow actinium, Z equals to 89. These are placed separately to avoid undue sidewise expansion of the periodic table. The elements in the first row starting from lanthanum are called lanthanides or lanthanoids, and the elements present in the second row starting from actinium are called actinides or actinoids. These lanthanides and actinides together are called inner transition elements or rare earth metals, and these are built up by filling of 4f orbitals. It is important to note from the above discussion that the first two groups, the last 6 groups, the 10 in between these two extremes and 14 small groups at the bottom of the periodic table correspond to the maximum number of electrons which may be added to s, p, d and f orbitals respectively. Discovery and nomenclature of elements with atomic number more than 100. The first scientific attempt to prepare the elements beyond uranium were made by Enrico Fermi and co-workers in 1934. They irradiated uranium with slow neutrons and found several radioactive products which are found to be due to new elements. The continued efforts of scientists led to many new elements. These were called transuranium elements. Today we have elements up to 112. These elements were earlier named traditionally by its discoverers or discoverers. However, in recent years, disputes regarding the original discoveries of some elements of atomic number 104 and above have arisen after several years of discussion by the Commission in Nomenclature of Organic Chemistry (CNIC) and comments of chemists around the world. IUPAC in 1997 gave the approved official names for elements with atomic number 104 to 109. However, the names of elements with atomic number 110 and above have yet to be officially announced. To solve the problem, IUPAC recommended a nomenclature to be followed for naming these new elements until their names are officially recognized. This nomenclature is based on the Latin word for their numbers. For example, nil for 0, un for 1, and so on as given below. Digit 0, root name nil, abbreviation N. Digit 1, root name un, abbreviation U. Digit 2, root name bi, abbreviation B. Digit 3, root name tri, abbreviation T. Digit 4, root name quad, abbreviation Q, and so on. The names are derived by combining together the roots in the order of digits which make up the atomic number, and EM is added at the end. For example, for atomic number 104, the name may be written as un for 1, nil for 0, quad for 4, and EM. Unil quadium, and is assigned the symbol U and Q. Full stop. At present, 114 elements have been discovered. These are elements with atomic number up to 112, 114, and 116. Elements with atomic number 113, 115, and 117 and 18 are not yet known. Of course, the quest of scientists to make new elements is continuing. The IUPAC name for the elements with atomic number more than 100 are given below. 101. Unil unium, 102, unibium, 103, unil trium, 104, unil quadium, 105, unil pentium, 106, unil hexium, 107, unil septium, 108, unil octium, 109, unil inium, and so on. Star represents the elements has been recently named. Classification of elements into S, P, D and F blocks. The long form of the periodic table can be conventionally divided into four main blocks. In this division, the elements which involve the filling of particular orbitals, that is S, P, D or F, are grouped together as shown in figure 1. S block elements. The elements in which the last electron enters the s orbitals of the outermost energy level are called S block elements. It consists of elements of group 1 and 2 having the ground state electronic configuration as ns1 and ns2 respectively. General configuration of S block elements is ns1 2 2. Now we move forward to p block elements. The elements in which the last electron enters the p orbital of the outermost energy level are called p block elements. The elements of group Roman number 3a or 13 to Roman number 8a or 18, involving addition of 1 ns2 np1, 2 ns2 npt np2, 3 ns2 np3, 4 ns2 np4, 5 ns2 np5 and 6 ns2 np6 respectively in p orbitals, and s orbitals are already filled in their atoms constituent p block elements. The general configuration is ns2 np1 to 6. D block elements. The elements in which the last electron enters the d orbitals of the last but not but one energy level constitute D block elements. This block consists of the elements lying between S and P block starting from 4th period and onwards. They constitute groups Roman number 3b to Roman number 8b and Roman number 1b and Roman number 2b or 3 to 12 in the periodic table. In this element, the outermost shell contains 1 or 2 electrons in their s orbital, but the last electron enters the last but 1d subshell, that is n-1d. The general electronic configuration may be written as n-1d, 1 to 10, ns1 or 2. Thus, it is the d orbital which is progressively being filled in elements of this block. These elements are called transition elements. The d block comprises 3 complete rows of 10 elements and 1 incomplete row. These rows are called first, second and third transition series, which involve the filling of 3d, 4d and 5d orbitals respectively. These series are also called transition series. Now we move forward to f block elements. The elements in which the last electron enters the f orbital of the atoms are called f block elements. In these elements, the last electron is added to the outermost called anti-penultimate energy level, that is n-2f. This consists of 2 series of elements placed at the bottom of the periodic table. The first series, as mentioned earlier, is known as lanthanum. That is atomic number 57, and the elements present in the series are called lanthanides. They are also called rare earth elements. The second series starts from actinium, atomic number 89, and they are known as actinides. They are radioactive in nature. The general configuration of S block elements is n-2 f1 to 14 and -1 d0 to 1 ns2. For example, for lanthanides, the general electronic configuration is 4f1 to 14 5d0 1 6s2, while for actinides it is 5f1 to 14 60 7s2. Now we discuss cause of periodicity. The recurrence of similar properties of the elements after certain regular intervals when they are arranged in the order of increasing atomic number is called periodicity. The classification of the elements in certain families was based upon the observed similarities in the physical and chemical properties. But why do certain elements exhibit similar properties, and why do the similar properties recur at regular intervals of atomic numbers, were some important questions yet to be answered. We know that an atom consists of nucleus surrounded by electrons. In ordinary chemical reactions, the nuclei of the atom do not undergo any change, and therefore it is the distribution of the electrons in the various shell of the atom that determine the physical and chemical properties of the elements. Thus, it must primarily be the arrangement of electrons in the outermost shell that determines the properties of the atom. For example, the electronic configuration of the atoms of alkali metals, table 2, shows that they all have one electron in the s orbital of the outermost valence shell, preceded by the noble gas configuration ns2 np6, but for lithium it is Ns2. The general electronic configuration of this may be written as noble gas Ns1, where N stands for principal quantum number. Thus, the cause of periodicity of the properties of elements is the repetition of similar electronic configuration of the atoms in the outermost energy shell after certain regular intervals. Periodic properties. There are many physical and chemical properties of elements which show periodic variation with atomic numbers. Some of these properties, such as valency, atomic size, ionization energy, and electron affinity, are directly related to the electronic configuration. Let us discuss some of this. First, we move forward to atomic radii. This is very important property because many physical and chemical properties are related to atomic radii. Generally, the term atomic radius means the distance from the center of the nucleus to the outermost shell of electron. If the atom is assumed to be spherical, it is the radius of the sphere. However, the absolute size of the atom is difficult to be defined because of the following reasons. According to the probability picture of electron, an atom does not have well-defined boundary. The probability of finding the electron is never zero, even at large distance from the nucleus. It is not possible to isolate an atom and measure its radius. The probability distribution of an atom is also affected by the presence of other atoms in its neighborhood. However, the size of atom may change in going from one set of environment to another. Thus, we can only arbitrarily define atomic radius as the effective size, which means the distance of closest approach of one atom to another atom in a given bounding situation. There are many atomic radii which are classified as covalent radius, van der Waals radius, ionic or crystal radius, etc. depending upon the type of bonding. First we discuss covalent radius. The radius of an atom is calculated by measuring the distance between the center of two atoms in molecule with the help of X-ray differentiation or spectral studies. In case of homonuclear diatomic molecules, the atomic radius is defined as one half the distance between the centers of nuclei of two similar atoms bounded together in a molecule. The radius is also called covalent radius because the atom in homonuclear diatomic molecule are held together by covalent bond. For example, the internuclear distance between two atoms of H2 molecule is 0.7 angstrom. Therefore, atomic radius of hydrogen will be 0.74 angstrom divided by 2, which gives us 0.37 angstrom. In case of heteronuclear diatomic molecules, it has been observed that when the covalent radii of different atoms joined by single covalent bond are added, the resulting value agrees fairly well with the experimentally determined internuclear distance of the molecule. For example, the internuclear distance of an HCl molecule can be calculated by adding the covalent radii of H and Cl. The calculated value of internuclear distance is in good agreement with the experimentally observed internuclear distance of 1.31 angstrom in HCl molecule. This process may be reversed, that is, the atomic radii of each atom may be calculated by subtracting the atomic radius of Cl from the internuclear distance of HCl molecule. In general, the atomic radius of one atom B in AB molecule can be calculated by measuring the internuclear distance RAB of AB molecule and knowing atomic radius of atom A as RB equal to RAB minus RA. The atomic radii of atoms which do not form diatomic molecules with single bond are calculated by indirect methods. For example, single bond radii of nitrogen and oxygen are not obtained from RAB, which gives us RA plus RB or modulus XA minus XB. The bond length in N2, N triple bond N and O2, O double bond O. Because these molecules contain multiple bonds, one half of the internuclear distance of these molecules will correspond to multiple bond radii. For example, the triple bonded radius of nitrogen is 1.10 divided by 2, which gives us 0.55 angstrom. The single bond atomic radius of nitrogen can be obtained by indirect method, multiple bond radii. For multiple bonded atoms, the corresponding radii are called multiple bond radii. For example, carbon has double bonded radius of 0.66 angstrom in ethylene and triple bonded radius that of 0.60 angstrom in acetylene. The carbon has single bond radius of 0.77 angstrom. Similarly, nitrogen has single, double and triple bond radius of 0.70 angstrom, 0.60 angstrom, and 0.55 angstrom respectively. Hybridization and atomic radius. The state of hybridization also affects the radius of an atom. For example, the carbon hydrogen single bond distance in methane CH4 sp3 hybridization, ethylene CH2 double bond CH2 sp2 hybridization, and acetylene CH triple bond CH sp hybridization is different, and therefore the atomic radius of carbon is different. For example, CH internuclear distance are CH4 1.14 angstrom, CH2 double bond CH2 1.11 angstrom, CH triple bond CH 1.07 angstrom. Hybridization sp2 s character will be 25%. Hybridization sp2 s character will be 33.3%. I might be mistaken as I pronounced hybridization sp3 as sp2. So sp3 s character will be 25%, sp2 s character will be 33.3%, and sp hybridization s character will be 50%. Since the atomic radius of hydrogen is 0.37 angstrom, the atomic radius of carbon in CH4, CH2 double bond CH2, and CH triple bond CH is 0.77 angstrom, 0.74 angstrom, and 0.70 angstrom respectively. The decrease in atomic radius of carbon or carbon-hydrogen internuclear distance may be attributed to the increase in s character in going from sp3 25% to sp2 33.3% to sp 50%. With increase in s character, the electron pair between C and H becomes closer to the nucleus, resulting in greater attraction, and therefore atomic radius decreases. We will discuss atomic radii in angstrom of main group S and P block elements. Hydrogen 0.7, helium 1.22, lithium 1.23, beryllium 0.89, boron 0.80, carbon 0.77, nitrogen 0.70, oxygen 0.66, fluorine 0.64, neon 1.60, sodium 1.57, magnesium 1.36, aluminium 1.25, silicon 1.17, phosphorus 1.10, sulfur 1.04, chlorine 0.99, argon 1.91, potassium 2.03, calcium 1.74, and so on. The value for atomic radii of noble gas are van der Waals radii rather than their covalent radii. Now we discuss next radius, that is metallic or crystal radius. This gives the size of atoms in case of metallic elements. In case of metals, a large number of atoms are closely packed and are held together by means of metallic bonds. The close packing of the metal atoms is known as crystal lattice of metallic lattice, and this packing is different in different metals. The metallic radius may be defined as 1/2 the distance between the nuclei of two adjacent atoms of a metal in a metallic lattice. The internuclear distance between the nearest neighboring atoms in metallic crystal is determined by X-ray diffraction. This is divided by 2 to calculate the metallic radius S. Radius metallic. Internuclear distance between two adjacent atoms in metallic lattice divided by 2. For example, the metallic radius of sodium is 1.86 angstrom. The metallic radii are larger than the corresponding single bond covalent radii. For example, the covalent radius of sodium is 1.54 angstrom, while its metallic radius is 1.86 angstrom. This is because metallic bond is weaker than covalent bond, and therefore the metal atoms in a metallic lattice are not drawn as close to each other as in covalent bond. Now we discuss van der Waals radius. Van der Waals radius is defined as 1/2 of the internuclear distance between the adjacent atoms belonging to two nearest neighboring molecules of the same substance in the solid state. It has been observed that there are some weak forces of attraction between the neutral atoms of noble gas atoms and non-polar molecules of various substances. These are known as van der Waals forces, and due to these forces the noble gas atoms and non-polar molecule are held together, particularly in the solid states. Thus the van der Waals radius corresponding to the closest approach of two atoms of noble gases or non-polar molecules of other substances which otherwise do not form bonds. The measurement of van der Waals radius for chlorine is shown as R van der Waals force. Internuclear distance between two non-bonded nearest neighboring atoms. Internuclear distance between two chlorine atoms of nearest neighboring molecule is 3.60 angstrom. Hence, van der Waals radius becomes 3.60 divided by 2, which gives us 1.80 angstrom. The van der Waals radius of some atoms are given in table 4 along with their covalent radii. The van der Waals radii are larger than covalent radii. This is obvious because in the formation of covalent bond, the atoms come close to each other due to overlapping of orbitals. On the other hand, van der Waals forces exist between atoms or molecules are weak and the atoms are at large distances. And hence, van der Waals radiuses are larger than covalent radius. Covalent and van der Waals radius in angstrom of some atoms. Elements N, O, F, Ne, P, S, Cl and Ar. Covalent radius 0.77, 0.74, 0.72 doesn't exist. 1.10, 1.04, 0.99 does not exist. Van der Waals 1.50, 1.40, 1.35, 1.31, 1.80, 1.90, 1.80, 1.74. Bragg-Slater radii. Bragg and Slater proposed set of internally consistent atomic radius. This radii can be added irrespective of the bond type involved in the interaction between two atoms to give good correlation with observed internuclear distance. In general terms, the Bragg-Slater radii represents the radii of inner cores of electron, which in turn determine how closely two atomic species and can approach each other. The Bragg-Slater radii of element of second periodic table are given ahead. Elements lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. Covalent radius in angstrom 1.23, 0.89, 0.80, 0.77, 0.70, 0.66 and 0.64. Bragg-Slater radius in angstrom 1.45, 1.05, 0.85, 0.70, 0.65, 0.60, 0.50. Now we discuss periodic trends in size. Variation of atomic radii in a period. In general, the atomic radii decrease as we move from left to right in a period in the periodic table. For example, in the second period, the atomic radii decreases from lithium to fluorine through beryllium, boron, carbon, nitrogen and oxygen. Explanation. This may be explained on the basis of increasing nuclear charge along a period. With the increase in atomic number from lithium to fluorine, the magnitude of the nuclear charge increases while the corresponding addition of electron takes place in the same principal shell. Since the electrons in the same shell do not screen each other from the nucleus, the increase in nuclear charge is not neutralized by the extra valence electron. As a result, electrons are pulled closer to the nucleus by the increased effective nuclear charge and thereby causes a decrease in the atomic radius. Note: the variation in atomic radii in periodic can easily be explained on the basis of effective nuclear charge, which is already discussed in Unit 1, instead of nuclear charge. Effective nuclear charge equals to actual nuclear charge minus screening constant. The effective nuclear charge increases secularly in a period as given below. Elements name lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. Nuclear charge 3, 4, 5, 6, 7, 8, 9. Effective nuclear charge 1.30, 1.95, 2.60, 3.25, 3.90, 4.55, 5.20. Variation of atomic radii in group. The atomic radii of element increases from top to bottom in group. Explanation. In moving down a group, the nuclear charge is increasing with increase in atomic number and we expect that the size of atom should decrease. However, while going from one atom to another, there is increase in the principal quantum level, although the number of electrons in the outermost shell remains the same. The effect of increase in the size of electron cloud is more pronounced than the effect of increased nuclear charge. Consequently, the distance of the outermost electron from the nucleus gradually increases down a group In other words, the size of the atom goes on increasing as we move down a group, as illustrated in table 6 for alkali metals. Elements and its electronic number. Lithium 2s1, atomic radius 1.23 angstrom. Sodium atomic number 11, outermost electronic configuration 3s1, 1.57 angstrom atomic radius. Similarly for potassium 19, 4s1, 2.03 angstrom. Rubidium 3s37, 5s1, 2.16, and so on. It is clear that the atomic radius increases down the group as discussed already in table 6. Ionic and crystal radii. The ionic radii correspond to the radius of ions in ionic crystal. The ions are formed as a result of addition or removal of electrons from the outermost shells of atoms. The ions formed by the loss of electron acquire positive charge and are called cations, while the ions formed by the gain of electron acquire negative charge and are called anions. Ionic radius may be defined as effective distance from the nucleus of the ion up to which it has influence in the ionic bond. Measurement of ionic radius. The X-ray studies gives the distance between the nuclei of adjacent positive and negative ions in the crystal. If the ions are regarded as spheres, the internuclear distance may be taken equal to sum of radius of the cation and the radius of the anion. For example, the internuclear distance of Na positive Cl negative is 2.76 angstrom, which corresponds to sum of ionic radii of Na positive and Cl minus ions. But the problem of assigning different values to constituting ions is not simple. Unless the radius of any one ion is known, we cannot calculate the radius of the other ion. Several methods have been proposed to calculate the ionic radii of ions. Out of the various methods, Pauling's method is most widely accepted. Now we discuss Pauling's method for calculation of ionic radii. This method is based on the calculation of ionic radii from the observed internuclear distances from a set of ionic compounds which have the cation and anion isoelectronic, that is, the cations and anions have the same number of electrons. He selected 4 ionic compounds: sodium fluoride, potassium chloride, rubidium bromide, and cesium iodide. In each salt, the cation and anion are isoelectronic. For example, in sodium fluoride, both Na positive and F minus ions have 10 electrons and have the configuration 1s2, 2s2, 2p6. Similarly, in KCl, Rb, Br, and CSi, the cations and anions have 18, 36, and 54 electrons respectively. Pauling suggested that the isoelectronic ions, the radius of an ion is inversely proportional to the effective nuclear charge Z effective of the ion, that is, R is inversely proportional to Z effective. R proportional to Z effective can also be written as Z minus S, where Z stands for nuclear charge, S stands for screening constant, or R is given as C upon Z minus S, where C is proportionality constant and it is same for two isoelectronic ions. The effective nuclear charge can be calculated by subtracting the screening constant from the actual nuclear charge. The value of screening constant is calculated from Slater's rule. Let us consider an example of sodium fluoride. The internuclear distance in NaF has been found to be 2.31 angstrom, so that radius of Na positive plus radius of F negative is equal to 2.31 angstrom. Both Na positive and F minus ions are isoelectronic, having 10 electrons and have the same value of screening constant. According to Slater's rule, the screening constant for both the ions have been found to be 4.15, that is S equals to 4.15. The actual nuclear charges of Na positive and F minus ions are 11 and 9 respectively, so that effective nuclear charge of Na positive becomes 11 minus 4.15, which gives us 6.85, and for fluorine F minus N minus 4.15, which gives us 4.85. Thus, according to Pauling, radius of Na positive gives us C divided by 6.85. Similarly, for F minus, the radius of F minus becomes C divided by 4.85. Substituting the value of radius of Na positive and radius of F minus in equation 1, which was, we get C divided by C 6.85 plus C divided by 4.85 2.31. The equation 1 was R Na positive plus Rf negative equals to 2.31 angstrom. So we substitute these values and get that equation. So 4.85 C plus 6.85 C gives us 2.31 multiplied by 6.85 multiplied by 4.85, which gives us 11.7 C equals to 76.74. Thus we get the C value of C as 6.56. So substituting these values of C in radius Na positive, we get radius of Na positive as 0.96 angstrom and radius for F minus we get 1.33 angstrom. With the help of above procedure, the radii of most of the cations and anions have been determined. Now we move forward to size of cation and anion. Size of the cation. In general, size of cation is smaller than the size of neutral atom. This is due to the fact that with the removal of electron from an atom, the magnitude of nuclear charge remains same while the number of electrons decrease. As a result, the nuclear charge now acts on lesser number of electrons. In other words, the effective nuclear charge per electron increases and the electrons are more strongly attracted and are pulled towards the nucleus. This causes a decrease in the size of atom. Size of cation and anion. In general, the negative ion or anion is always larger than that of corresponding atom. The negative ion is formed by the gain of one or more electron in the neutral atom, and the number of electrons increase while the magnitude of nuclear charge remains the same. As a result, the same nuclear charge acts on large number of electrons than present in the neutral atom. In other words, effective nuclear charge per atom is reduced and the electron cloud is held less tightly by the nucleus. This causes an increase in size and thus anions are larger in size than the corresponding atoms. The ionic radii of some compounds of S and P blocks are given in table 7. Ionic radii angstrom of ions of S and P block elements with noble gas configuration. Hydrogen 1.54 angstrom, lithium positive 0.60, beryllium 2 positive 0.39, boron 3 positive 0.20, carbon 4 positive 0.15, nitrogen 5 positive 0.11, oxygen 6 positive 0.09, oxygen 2 negative 1.40, fluorine negative 1.36, sodium positive 0.95, magnesium 2 positive 0.65 and so on. Periodic trends in ionic radii. Variation of ionic radii in a period. For an isoelectronic series, ions having same number of electrons, the ionic radius decreases as the nuclear charge increases. Explanation. In an isoelectronic series, there is an increase in nuclear charge and therefore the attraction for the same number of electrons increases. As a result, the electrons are pulled more and more strongly and this ionic radius decreases. All ions have configuration containing 10 electrons. Table 8. Variation of ionic radii in an isoelectronic series. Ion N3 minus nuclear charge plus 7, radius in angstrom 1.72. Oxygen 2 minus nuclear charge plus 8, radius in angstrom 1.40. Fluorine minus nuclear charge plus 9, radius in angstrom 1.26 and so on. Variation of ionic radii in group. As we go down a group, the ionic radii increases with increase in atomic number. This is because due to increase in the principal quantum levels. The effect of increase in principal quantum level is more pronounced than the effect of increased nuclear charge. Table 9. Variation of ionic radii in group Roman number 1A elements. Li positive 0.60, Na positive 0.95, K positive 1.33, Rb positive 1.48, Cs positive 1.69. Explanation. This is mainly due to increase in the principal quantum levels. The effect of increase in principal quantum number is more pronounced than the effect of increased nuclear charge. Now we move forward to ionization energy. Ionization energy gives a measure of the ease with which an atom can lose an electron and change into cation. Ionization energy of an element is defined as amount of energy required to remove the most loosely bound electron from an isolated gaseous atom. Mg positive, for example, plus ionization energy Mg positive gas plus electron in gaseous state. Ionization energy is also called as ionization potential because it is measured as the amount of potential needed to remove the most loosely held electron from the gaseous atom. The experimental values of ionization energies are determined either by spectroscopic methods or by passing an electric current or of gradually increasing intensity through the various vapors of the elements in a discharge tube. It is expressed in terms of either in kcal per mole or kilojoule per mole or electron volt per atom. Thus, the ionization energy gives the ease with which electron can be removed from an atom. Factors on which ionization energy depends. The magnitude of ionization energy for an atom depends upon following factors. Size of atom. Ionization energy depends upon distance between the electron and the nucleus, that is size of the atom. The attractive force between electron and the nucleus is inversely proportional to the distance between them. Consequently, as the size of atom increases, the outermost electrons are less tightly held by the nucleus. As a result, it becomes easier to remove the electron and therefore ionization energy decreases with the increase in atomic size. Charges on the nucleus. The attractive force between the nucleus and the electron increases with increase in nuclear charge. This is because the force of attraction is directly proportional to the product of charge on the nucleus and that on the electron. Therefore, with increase in nuclear charge, it becomes more difficult to remove an electron and ionization energy increases. Screening effect. In multi-electron atoms, the outermost electrons are shielded or screened from the nucleus by the inner electron. This is known as shielding or screening effect. As a result of this, the outermost electron does not feel the full charge of the nucleus. The actual charge felt by electron is termed as effective nuclear charge. Effective nuclear charge equals to total nuclear charge Z minus screening constant, where screening constant takes into account the screening effect of the inner electrons. If the number of electrons in the inner shell is large, the screening effect will be large. As a result, the nucleus electron force will be less, and that's why the ionization energy will be less. Penetration effect of the electrons. It is well known that in case of multi-electron atoms, the electrons in the s orbital have the maximum probability of being found near the nucleus, and this probability goes on decreasing in case of p, d and f orbitals. In other words, s electrons are more penetrating towards the nucleus than p electrons, and the penetration power decreases in a given shell. Same value of n in the order s greater than p greater than d greater than f. Now, if the penetration of the electron is more, it will be closer to the nucleus and will be held firmly. Consequently, ionization energy will be high. This means that ionization energy increases with the increase in penetration power of the electron. Thus, for the same shell, the required ionization energy would be more to remove an s electron than to remove a p electron, which in turn will be more than for the removal of d electron, and so on. Electronic arrangement. The ionization energy also depends upon the electronic configuration of the atom. It has been observed that certain electronic half-filled and completely filled shells have extra stability associated with them. Consequently, it is difficult to remove electron from these stable configurations, and ionization energy is high. This may be illustrated by the following examples. The noble gases have the most stable electronic configuration in each period and have highest ionization energies. The elements like beryllium 1s2 2s2 and Mg 1s2 2s2 2p6 3s2 have completely filled orbitals and their ionization energies are large. The elements like nitrogen 1s2 2s2 2p1 2p1 2p1x 2p1y 2p1z and p potassium phosphorus 1s2 2s2 2p6 3s2 3px1 3py1 3pz1 have configuration in which orbitals of same subshell are exactly half filled and are also stable. Hence, they also need high ionization energy. Thus, more stable the electronic configuration, the higher will be the ionization energy. Variation of ionization energy in the periodic table. Ionization energy provides another example for understanding periodic among the elements. The ionization energy of elements of S and P blocks are given in table number 10. Hydrogen 1312.0, helium 2372.1, lithium 520.3, beryllium 899.5, boron 800.6, carbon 1086.4, so nitrogen 1402.1, oxygen 1314.0, fluorine 1681.0, neon 2080.4, and so on. The variation of first ionization energy of elements with atomic number up to atomic number 60 is shown in figure 5. It can be seen from figure 5 that in each period the maxima are found at the noble gases while minima are found at alkali metals. Thus the metals of group Roman number 1 with 1 electron in outermost orbitals are easy to ionize, while the noble gases group Roman number 8a with NS2 and P6 configuration are the most difficult to ionize. The following periodic trends have been observed. Variation along a period. In general, the ionization energy increases with increasing atomic number in period. This is quite clear from the values of ionization energy of the second row elements as given in table 11. The general increase along a period can be explained on the basis of atomic size and nuclear charge. We know that on moving across a period from left to right, the nuclear charge increases. The atomic size decreases along a period through energy level remains the same. As a consequence of increased nuclear charge and simultaneous decrease in atomic size, the valence electrons are more and more tightly held by the nucleus. Therefore, more and more energy is needed to remove the electron, and hence ionization energy keeps on decreasing. Table 11. Ionization energies of the elements of second period. Elements: lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. Atomic number 3, 4, 5, 6, 7, 8, 9, 10. Electronic configuration 1s2, 2s1, 1s2, 2s2, 1s2, 2s2, 2p1, 1s2, 2s2, 2p2, 1s2, 2s2, 2p3, 1s2, 2s2, 2p4, 1s2, 2s2, 2p5, 1s2, 2s2, 2p6, and the respective ionization energy in kilojoule per mole: 520.3, 899.5, 800.6, 1086.4, 1402, 1314, 1684, and 2080. However, some irregularities in the general trend have been noticed. These are due to half-filled and completely filled configuration, which have extra stability. To illustrate this, let us consider the variation of ionization energy in second period, going from one element to another. Lithium to beryllium. On moving from lithium to beryllium, there is an increase in ionization energy, and this is due to increased nuclear charge and smaller atomic size. From beryllium to boron. Although the nuclear charge of boron is more than beryllium, yet there is slight decrease in ionization energy from beryllium to boron. This is due to the fact that in boron, last electron goes to 2p orbital, which is at a slightly higher energy level than 2s and is easy to be removed. The electronic configuration of boron 1s2, 2s2, 2p1 is less stable than that of beryllium 1s2, 2s2, which has completely filled orbital. As a result, the 2p electron of B is not tightly held by the nucleus as 2s electron of beryllium, and hence ionization energy of boron is less than that of beryllium. Boron to carbon to nitrogen. As we move from boron to carbon and from carbon to nitrogen, the ionization energy keeps on increasing due to increased nuclear charge and the decreasing atomic size. From nitrogen to oxygen, the element next to nitrogen has slightly smaller ionization energy as compared to that of nitrogen. It is due to the fact that electronic configuration of nitrogen atom 1s2, 2s2, 2px1, 2py1, 2pz1, in which each 2p orbital is half filled, is more stable than that of oxygen 1s2, 2s2, 2px2, 2py1, 2pz1. Therefore, ionization energy of nitrogen is more than that of oxygen. Oxygen to fluorine to neon. The ionization energy increases from oxygen to fluorine to neon because of the increased nuclear charge and decrease in size. Neon, the noble gas has the maximum ionization energy in the period due to stable NS2 and P6 electronic configuration. Similar variation in ionization energies of the elements of third period have also been observed. Variation down a group. Within a group, there is gradual decrease in ionization energy in moving from top to bottom. This is clear from the ionization energy values of the elements of the first group, as given in table 12. In table 12, we discuss ionization energy of the elements of first group. Elements: lithium, sodium, potassium, rubidium, cesium. Outermost energy shell configuration: 2s1, 3s1, 4s1, 5s1, 6s1. Ionization energy in kilojoule per mole: 520.3, 495.8, 418.9, 403.2, 374.1. This decrease in ionization energy down a group can be explained in terms of net effects of the following factor. In going from top to bottom in a group, the nuclear charge increases. There is gradual increase in atomic size due to additional main shell N. There is an increase in shielding effect of the outermost electron due to an increase in the number of inner electrons. The effect of increase in atomic size and the shielding effect is much more than the effect of increase in nuclear charge. As a result, the electron becomes less and less firmly held to the nucleus as we move down the group. Hence, there is gradual decrease in the ionization energies in a group. Successive ionization energy. The atom may not only lose one electron but more than one electrons also. Therefore, it is essential to specify the definition of ionization energy for each electron which is to be removed. The energies required to remove subsequent electrons from the atom in the gaseous state are known as successive ionization energies. The term first, second, third ionization energy refers to the removal of first, second, third, and so on electrons respectively. These changes may be represented as follows: M in a metal, G its state, ionization energy 1, M positive plus electron, M positive ionization energy second, M2 positive plus electron, M2 positive ionization energy third, M3 positive plus electron. Here IE1, IE2 and I3 represent first, second and third ionization energies respectively. For example, the first and second ionization energies for lithium may be given as Li, lithium, state gaseous. Due to ionization energy 1, it converts into Li positive in the gaseous state plus 1 electron. Here ionization energy 1 is 520 kJ per mole. Similarly, when Li positive is again ionized, the ionization energy is 7298 kJ per mole. As can be seen, the second ionization energies are very much larger than the first ionization energies. This is mainly due to the fact that after the removal of first electron, the atom changes into monovalent positive ion. In the ion, the number of electrons decreases but the nuclear charge remains the same. As a result of this, the remaining electrons are held more tightly by the nucleus and it becomes difficult to remove the second electron. Hence, the value of second ionization energy is greater than that of first. In the same way, the removal of second electron may result in the formation of dipositive ion and attraction between the nucleus and remaining electron increase further. This result into higher value of third ionization energy. The successive ionization energy of first 14 elements is shown in table 13. The ionization energies to the right of the stepwise lines correspond to removal of electron from field configuration of the atom. As is clear from the table, to each atom there is large increase in energy after all the outermost electrons have been removed. For example, in case of sodium, the first ionization energy is 496 kJ per mole, but second ionization energy is 4564 kJ, that is almost 10 times. Similarly, for magnesium, first ionization energy is 737 kJ per mole and second ionization energy is 1447 kJ per mole. However, third ionization energy value is 7738 kJ per mole, which is over 5 times than the second ionization energy. This is because after all the electrons in the valence shell have been removed, the next electron must be removed from the core of the atom, having stable noble gas configuration. Therefore, ionization energy becomes much and much higher. Table 13 shows successive ionization energy in kilojoule per mole. Elements: hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, magnesium, aluminum, silicon. First ionization energy: 1312, 2372, 520, 899, 801, 1086, 1402, 1314, 1681, 2080, 496, 738, 577, 786. Second ionization energy. Hydrogen doesn't possess any second ionization energy. It starts with helium. 5250, 7298, 1757, 2427, 2353, 2856, 3388, 3374, 3952, 4564, 1451, 1817, 1577, and so on goes on with third ionization energy, fourth, fifth, sixth, seventh, up to eighth. Now we come to the next topic, which is electron affinity. Just as energy is required to remove an electron from an atom, energy is required when an electron is added to a neutral atom. This is called electron affinity, which is represented by EA. Thus, the amount of energy released when an electron is added to an isolated gaseous atom is called electron affinity. The process may be expressed as X, which represents any metal. Its state is gaseous plus electron, X negative plus energy, electron affinity. As definition implies, the magnitude of electron affinity measures the stability of an atom. To hold an additional electron. If an atom has more tendency to accept an electron, larger energy will be released. Consequently, electron affinity will be high. On the other hand, if an atom has less tendency to hold an electron, small amount of energy will be released, leading to small value of electron affinity. Electron affinities can be positive or negative. When energy is released during the addition of an electron of an atom, the electron affinity is taken as positive. Electron affinities are expressed in kilojoule per mole. Factors on which electron affinity depends. Nuclear charge. The electron affinity increases as the nuclear charge increases. This is due to greater attraction for the incoming electron if nuclear charges is high. Size of atom. With increase in size of atom, the distance between two nucleus and the incoming electron increases, and this results in lesser attraction. Consequently, the electron affinity value will decrease. Electronic configuration. The elements having stable electronic configuration of half and completely filled valence subshells show very small tendency to accept additional electron, and thus electron affinities are low or almost zero in certain cases. Periodic trends. Due to lack of sufficient data, the changing trends in electron affinities on moving along the periodic table are less well defined than those for ionization energies. However, it has been observed that electron affinity in general increases from left to right in a period and decreases from top to bottom in group. These variations are discussed below. Variation down a group. On moving down a group, the atomic size and nuclear charge increases, but the effect of increase in atomic size is much more pronounced than that of nuclear charge, and thus the additional electron feels less attraction by the large atom. Consequently, electron affinity decreases. This is clear from the decrease of electron affinity in going from chlorine to bromine and to iodine. Variation along a period. On moving a period, the size of atom decreases and nuclear charge increases. Both these factors result into greater attraction for the incoming electron. Therefore, electron affinity in general increases in a period from left to right. However, certain irregularities are observed in the general trend. These are mainly due to stable electronic configuration of certain atoms. There are some important features of electron affinities of elements. These are: halogens have highest electron affinities. The electron affinity of the halogens group Roman number 7a elements are the highest. This is due to the fact that halogens have general electronic configuration of ns25 and have only one electron less than stable noble configuration. Thus, they have very strong tendency to accept an additional electron, and their electron affinities are therefore really very high. Electron affinity of noble gas are 0, while those of beryllium, magnesium, nitrogen and phosphorus are almost 0. The electron affinity of noble gases are 0. This is because they already have stable electronic configuration of ns26, and thus they have absolutely no tendency to take an additional electron. This means the incoming electron does not feel any attraction for the nucleus. Similarly, the low, that is almost 0 electron affinity value for beryllium, magnesium, nitrogen and phosphorus can be explained due to the extra stability of fully filled 2s and 3s orbitals in beryllium and magnesium respectively, and of half-filled 2p and 3p orbitals in n and p respectively. Electron affinity of fluorine is unexpectedly less than that of chlorine. As already explained, the electron affinity in general decreases from top to bottom in a group. However, it is observed that F atom has unexpectedly less electron affinity than chlorine atom. The electron affinity value for the halogen are shown in figure 7. The low value of F atom is due to very small size of F atom. As consequence of small size, there are stronger inter-electronic repulsion in a relatively compact in the relatively compact 2p subshell of fluorine, and thus the incoming electron does not feel much attraction. As a result, the electron affinity value is small. On the other hand, the electron affinity of Cl atom is larger than F atom, where the electron is added to the relatively larger 3p orbital, which can easily accommodate the additional electron. It may be noted that in general the electron affinities for some third period elements, example phosphorus, sulfur, chlorine, are greater than corresponding second period member, that is nitrogen, oxygen and fluorine respectively. This is due to smaller size of atom of the second period elements, which would produce larger electron repulsion for the additional electron. This effect is much more pronounced in the smaller fluorine atom as discussed above. Successive electron affinities. Like ionization energies, the second and higher electron affinities are also possible. However, the second electron is added to negatively charged and the additional is opposed by Coulombic repulsion. The energy has to be supplied to force the second electron as shown below for oxygen. Oxygen plus electron O negative, electron affinity 140.9 kilojoule per mole, energy released. Oxygen negative plus electron O2 minus, electron affinity second minus 770 kilojoule per mole, energy is required. In other words, the second and higher electron affinities would have negative values, since the first electron affinity in which energy released is taken as positive. For example, the first and second electron affinity of O and S are: for oxygen, electron affinity 140.9 kilojoule, electron affinity second minus 770 kilojoule. For sulfur, 200.7 kilojoule, and second is minus 333 kilojoule. Electronegativity. Now we come forward to next topic. When a covalent bond is found between two homonuclear atoms, the shared pair of the covalent bond is exactly midway between the nuclei of the two atoms, because both the atoms may have same attraction for this electron. For example, in molecules such as H2Cl2F2, the electron pair remains exactly at half distance between the two nuclei. However, in case of covalent bond between dissimilar atoms, the electron pair may be closer to one another than the other. Different atoms have different tendencies to attract bond pair electron towards themselves. The tendency of an atom to attract the shared pair of electron in a molecule towards itself is called electronegativity. Greater the ability of an atom to attract electrons in a bond, larger is the value of its electronegativity. It must be remembered that unlike other atomic properties such as ionization energy and electron affinity, which are related to individual gaseous atoms, the electronegativity is related to the atom in their bonded state. There is no direct method of measuring electronegativity. However, various attempts have been made to derive a scale of electronegativity for the elements. Some of them are discussed below. The first one is Pauling scale of electronegativity. Now we come forward to the next topic, that is Pauling scale of electronegativity. In 1932, Linus Pauling was the first to propose a scale of electronegativity. He proposed the scale based on the bond energies in heteronuclear bonds. He suggested that if two atoms A and B had the same electronegativity values, the bond energy of the AB bond would be equal to the geometric mean of bond energy of AA and BB bond. For example, the bond energy of AB molecule may be written as EAB equals to EAA cross EBB whole to the power 1 by 2. This relation is based on the assumption of pure covalent bond of A2 in A2 and B2 and AB molecule. However, he observed that for most of the AB bonds, the actual bond energy is more than the geometric mean of bond energy of EAA and EBB. This means that two participating atoms have different tendencies to attract the shared pair, that is, have different electronegativities. In other words, the bond AB will no longer be purely covalent bond. As a result, there is contribution of ionic structure A plus and B minus, in addition to pure covalent AB structure. The difference between the actual bond energy of AB, EAB and the geometric mean bond energy EAA cross EBB 1 by 2 is known as excess bond energy, which is represented by delta E. It is measure of the difference in electronegativities of two atoms A and B. Thus, delta E equals to EAB minus in bracket EAA cross EBB raised to the power 1 by 2. The excess bond energy arises due to resonance between the structure AB covalent and A plus B minus ionic and is also known as ionic resonancy energy. By calculating delta E for different bonds, Pauling suggested the following type of relation between electronegativities of two atoms. Assume XA and XB and the excess bond energy delta A, that is XA minus XB equal to 0.18 times delta E whole to the power 1 by 2, where delta A is excess bond energy in kCl per mole. Assigning an arbitrary value to one of the elements, the electronegativities of other elements could be easily calculated. Pauling assigned the value of 4.0 to the most electronegative element, fluorine. The Pauling electronegative values are given in table 15 for normal elements. These are most commonly used values. Hydrogen 2.1, lithium 1.0, sodium 0.9, potassium 0.8, rubidium 0.8, cesium 0.7, beryllium 1.5, magnesium 1.2, calcium 1.0, strontium 1.0, boron 2.0, aluminium 1.5, gallium 1.6, indium 1.7, helium 1.8, carbon 2.5, silicon 1.8, germanium 1.8, tin 1.7, lead 1.7, nitrogen 3.0, and so on. Disadvantages of Pauling scale. The main disadvantage of Pauling scale is that the bond energies are not known with good degree of accuracy for many elements. However, the values are relative values. Now the second topic is Mulliken concept of electronegativity. Mulliken in 1934 suggested that the tendency of an atom to compete for the shared pair of electron in a bond should be the average of ionization energy and electron affinity. Ionization energy, i.e. electron affinity, EA. Thus, according to Mulliken, electronegativity of an atom equals to ionization energy plus electron affinity divided by 2, where both ionization energy and electron affinity are given positive value. The physical picture of Mulliken concept is reasonable because the tendency of an atom to attract shared electrons in a bond should be average of tendency of atom to hold its own electron and its tendency to attract additional electron. The Mulliken value expressed in electron volt have been found to be about 2.5 times as larger as Pauling value. Therefore, these values are divided by 2.8 to get Pauling value, that is x Pauling equals to x time Mulliken divided by 2.8. However, if IE and EA values are represented in kilojoule per mole inverse, 1 electron volt equals to 1.602 into 10 to the power minus 19 into 6.022 into 10 to the power 23 joule mole inverse, which equals to 96.48 kilojoule mole inverse. Pauling value can be expressed as x Pauling equals to x Mulliken by 2.8 into 96.48. Disadvantages of Mulliken scale. There are two main disadvantages of this scale. Electron affinity value of only a few elements are known. The ionization energy and electron affinity value change with valence state of element. Allred and Roche scale. The concept is based on the electrostatic force of attraction between an electron and its nucleus. The force of attraction is taken as measurement of its electronegativity. The force of attraction between the nucleus of the atom and its valence electron is governed by Coulomb's law and is given by force equal to Z star E into E by R square, where E equals to charge of electron, Z star effective nuclear charge, R mean distance from the nucleus, that is R covalent. The effective nuclear charge can be easily calculated by using Slater rule for screening of inner electrons. The force calculated from above equation were plotted against Pauling scale. From this plot, the following relationship is obtained: x equal to 0.359 Z star by R square plus 0.744. Disadvantages of Allred and Roche scale. The main disadvantages of the scale are the covalent radii of many elements are not available and Slater rule for calculating effective nuclear charge is empirical. However, the scale gained importance because it does not contain quantities such as electron affinity, bond dissociation energy, which are known for comparatively lesser number of elements. The next topic is Sanderson's scale of electronegativity. Sanderson proposed a scale of electronegativities based on compactness of the electron clouds around the nucleus or average electron density of an atom. The average electron density of an atom may be given as D equals to 3Z upon 4 pi R square, where R equal to covalent radius in angstrom, Z nuclear charge. According to Sanderson, the electronegativity is expressed as stability ratio for an atom. The stability ratio is defined as the ratio of average electron density of the atom to that of ideal electron density of hypothetical isoelectronic inert gas atom. Thus SR equal to D upon Di, where D is electron density of atom, Di ideal electron density of hypothetical noble gas having the same number of electrons. The stability ratio of an atom is the measure of its electronegativity. The SR values are similar to electronegativity value obtained by Pauling. These are adjusted to Pauling electronegativity X by the equation X की power 1 by 2, 0.21 SR plus 0.77. It may be noted that none of electronegativity scale discussed above has a distinct advantage over the other. For the comparison, the electronegativity value calculated by various methods are given. However, Pauling scale has been most commonly used, and in our further discussion, this value will be used. Element H, Pauling's 2.20, Aldred-Rocho 2.20, Mulliken doesn't have any values, Henderson 2.31. For lithium, Pauling's 0.98, for Aldred-Rocho 0.97, for Mulliken it's 1.3, and for Sanderson it's 0.86. For beryllium it's 1.17 for Pauling, for Aldred-Rocho it's 1.47, for Mulliken it does not have any value, and for Sanderson it is 1.61, and so on it carries. Now we have Mulliken and Jaffe scale. Mulliken and Jaffe also proposed a new scale which take into account the role of hybridization while calculating the electronegativities based on ionization energy and electron affinity. However, it has not been discussed in the present text. Factors affecting electronegativity. Electronegativity of an atom is not a fixed quantity but depends upon large number of factors both of isolated as well as bonded atoms. Some of the important factors affecting electronegativity values are given ahead. Oxidation state. The electronegativity of an atom varies from one bonding state to another depending upon the oxidation state of an atom in the molecule. In general, electronegativity increases as positive oxidation state of an atom increases. This is obvious because with the increase in positive oxidation state, the tendency to attract the electrons will increase. For anions, however, the electronegativity decreases with the increasing negative charge of the ion. This is due to the fact that a more negatively charged ion will attract less electron than a less negatively charged or neutral ion. Type of hybridization. The type of hybridization also affects the electronegativity of an atom. We have learned that s orbital are nearer to nuclei than p, d, f orbital because of their higher penetration power. Therefore, s orbital will have greater electron attracting power or electronegativity. In other words, the electronegativity increases with increase in s character of hybrid orbitals. This can be easily illustrated by taking the example of carbon. For hydrocarbon methane CH4, type of hybridization sp3, s character is 25%, electronegativity is 2.48. For ethylene, that is C2H4, type of hybridization is sp2, s character is 33%, electronegativity is 2.75. For acetylene C2H2, type of hybridization is sp, s character is 50%, electronegativity is 3.29. The s character increases in the order CH4, C2H4 and C2H2, and the electronegativity of carbon in this compound also increases. Nature of the substituents. The electronegativity of group varies with the nature of the substituents. This is due to the inductive effect of the substituent group. For example, for CH3 it is 2.30, for CCl3 it is 3.30, and for CF3 it is 3.35. In these cases, the electronegativity of this group will be the electronegativity of carbon as it is adjusted by the presence of substituents 3H, 3Cl or 3F atoms. These values are based on dipole moment, atomic electronegativity and kinetic data. Now we have periodic variation of electronegativity. The electronegativity generally increases on moving across the period from left to right. This is primarily due to decrease in atomic size and increase in effective nuclear charge. As a result of increase in effective nuclear charge, the attraction for the electron increases. Electronegativity generally decreases from top to bottom in a group as atomic size increases and the bonding electron become away from the nucleus. Thus, alkali metals of group Roman number 1 have the lowest electronegativities and halogens of group Roman number 7 have the highest electronegativities. Further inspection of table 2.14 shows that non-metals on the right side of periodic table have high electronegativity while the metal on left side have low electronegativity. In general, as an approximation, elements with electronegativity 2.0 or greater are non-metals, while those with electronegativity less than 2.0 are non-metals. Now there are some examples which is suggested to the students that they can attempt this question by themselves. So the theoretical part of the chapter comes to an end, And so now we will discuss some of the questions which are discussed in university exams. The electron affinity value of halogen decreases in the order fluorine to chlorine and from chlorine to bromine and bromine to iodine. Comment on the statement. The statement is wrong because the actual order is chlorine to fluorine and from fluorine to bromine and from bromine it is iodine. In general, electron affinity decreases down the group, but F has abnormally low electron affinity than chlorine because of its small size. Arrange the following in the decreasing order of electron affinity: boron, carbon, nitrogen, oxygen. So the correct order in decreasing order will be oxygen, carbon, boron and nitrogen. Now there is question: explain. Electron affinity value of 18th group element are 0. The electron affinity of 18th group element are 0 because these elements have stable electronic configuration of ns2 and p6. Therefore they have no tendency to accept an additional electron. Thus no energy is released and their electron affinities are 0. Successive electron affinity have negative values. After the addition of an electron, the anion formed has negative charge. Therefore the second electron has to be added to the negatively charged ion, and addition is opposed by Coulombic repulsion. Therefore energy has to be supplied to force the second electron. In other words, second electron affinity would have negative values. Next question is, which has the smaller size and why? This question was asked in Kurukshetra University in the year 2017. The previous question discussed was asked in Maharshi Dayanand University in the year 2000. H minus or HE? We have to answer which is smaller size. He. Both are iso, so the answer goes He, helium. Both are isoelectronic, but helium has higher nuclear charge than hydrogen, and therefore attraction for the electrons increase. As a result, electron cloud contrast more than in case of H minus ion. Nitrogen or oxygen? Oxygen. This is because oxygen has higher nuclear charge than nitrogen, which attracts the outer electrons more strongly than in the case of nitrogen. How does electronegativity in a given hybridization change with substituents? Electronegativity of an atom in given hybridization state in general increases. With increase in electronegativity, substituents are given below. CH3 it's 2.30, for CCl3 it's 3.30, and for CF3 it's 3.35. And the next question is, define electron affinity, which is larger electron affinity, and why chlorine or fluorine. Electron affinity is the amount of energy released when an electron is added to the gaseous isolated state of an atom. It may be expressed as x g plus electron in g, x minus g plus energy ea, electron affinity. Out of fluorine and chlorine has large electron affinity. This is because fluorine has abnormally low electron affinity because of its very small size. As a result of small size, there are strong inter-electronic repulsion in the relatively compact 2p subshell of F, and therefore incoming electrons feel less repulsion. So this was an end to the chapter periodic properties. We have read all the theoretical concept and discussed some of the questions which are asked in university exam. So that was all for today's video. Thank you all, and subscribe my channel for more such